So shall we start? Hi everyone. So I hope everybody's doing well. So yeah, I guess we should. So yeah, last time we ended up with the classification problem. I mean, we consider the binary classification problem. And there we wanted to do a binary classification of a bunch of images. So we had a bunch of images, handwritten numbers, and then wanted to know whether one image is a handwritten number 2 or not, right? So this was the problem. It was a binary classification. So you give an image, which is image of number 2, or any other handwritten number, and then you wish that your neural network at the end of the day gives you 1 if you have handwritten 2 as the input, but it's going to give you 0 if you input any other handwritten number or any other image, right? So this was the problem that we talked about, and we actually started with doing a quite basic approach. So do you remember before we start doing the modification, what was the output layer? So what was our initial approach for putting an output layer? It was a perceptron, right? And then when we wanted to just train that perceptron, what kind of loss function we considered? It was the indicator. Great. So we had indicator, we had perceptron, and then we got into trouble. What was the trouble? We couldn't calculate the derivative, right? It's because like these functions do not have derivative. So what did we do? We replaced both of them with two different things. The sigmoid function, great, and the cross entropy or MSE loss, right? So these were the modification that we did, and then we said that we should now interpret the output of the neural network, this guy, to be a kind of probability. So this y3, which is the output, is not anymore 0 or 1, is a number between 0 and 1, and it's going to give you the chance of your input being number 2 or anything else, right? Clear? So this was the idea, and then now with this guy, we could do simply the training, because if we just write down the backpropagation algorithm, we're going to see every single component that we need in this arg, or every single backward path that we need to do now is computable, right? So this was the idea, and then we said, okay, what if we want to now extend the idea to a case with multiple classes, right? So instead of just doing classification of number 2 or anything else, we now want to just find out the given written digit, whether it is 0, 1, 2, till 9, okay? So we have now 10 different classes. And initially when we started with the problem of classification, I told you that you can actually impose any classification problem as a sequence of binary classifications, right? So you could train a neural network which is going to tell you whether this is number 0, digit 0, or not, right? If it is 0, the classification is over. If it is not, then you need another neural network to check whether it is 1 or anything else, right? And then you need the next one to just tell you whether it is 2 or anything else. And you keep on going till number 9, right? But then in that case, you don't have just a single neural network. You have a sequence of neural networks, right? And this is not a very cool idea. I mean, it doesn't sound like something practical. So a better idea is to just extend what we did with the binary classification to a more general scenario with multiple classes. Meaning that instead of computing, I mean, we just had one single neuron here with sigmoid, and the key factor was that it could compute some number y3, which was of the nature of probability, right? It's going to tell us whether this is digit 2 or not, right? Probability. Now, if I have 10 classes, then I can think of a random thing, which could be with some chance in class 1, with some chance in class 2, and so on till class 10, right? And then if I can generate that probability vector, then I can just train my neural network to give me the right probability output, and then I'm going to take the class which has the highest probability. So we can basically extend this idea to a more general class where we have a vector of outputs. Okay? So I do still have 2 different layers. So if you remember, we started with 3 different layers, 1 output and 2 hidden layers in our architecture. And then I still start with my input vector or input data, which is an image in this case. And then I give it to first layer, then second layer, and then at the output, instead of computing just a single number with a single neuron, I want to compute a vector of numbers, right? Clear what I want to do? So I want to compute those numbers, and what I want that those numbers are again of the nature of probability. So if they are probability, what should they do? They should sum to 1, great, and one thing else? Between 0 and 1, exactly. So they should be between 0 and 1, and they should just add up to 1, right? So I want to have something like this. So this idea is what we call it vector activation, okay? And the vector activation is basically just extending the idea of simple neuron to a case where you have a kind of multi-dimensional neuron. So this is what I'm going to call it vector-activated neuron. It's not a kind of general term, but you can find it here and there. Okay? So you could have, like in some texts, you can see this vector-activated neuron, but some people don't call it that. I would call it because it's of the same nature. So what is a vector-activated neuron? It's again a neuron, artificial neuron, but the only difference is that instead of computing one single number as the output, it's now computing a vector as the output. So if you remember when we had a simple neuron, so the simple neuron, which we show it like this, and we put function f here. So if I have multiple edges just getting connected to this guy and one edge at the output, what would I say? I would say, okay, these are the inputs. Say, for example, in this case, I am giving to this guy x1, x2, and so on till xn. And how do I compute the output? Exactly. Yes. And since it is a single neuron, there is just a weight vector, right? So I'm going to just multiply the weight vector w to my input x. So now these are vectors. And then I add something else, which is a bias. It's a number, right? So I linearly transform the input x1 to xn into one number, right? So this is the number that we call it z, usually, right? And then here I do have y, and this y is simply the activated version of z, right? So this was a single neuron. Now, if I want to make it vectorized, what should I do? Instead of computing one simple number, I should calculate a vector here, right? And then instead of having a scalar function, I need to have a vectorized function. Clear? Now, what I'm going to do, instead of computing now, I am just replacing it with a vectorized form. So I'm going to put here a function f. Now I'm just writing capital function to indicate this is vectorized. And now, what I do compute, I am going to have, instead of, in the neuron, I had a vector here. Now, instead of a vector, I do have a matrix, right? So instead of this simple vector here, I'm going to have one matrix W, which is getting multiplied with my input. It's going to compute one output. I can potentially have a bias, but this bias now should be a vector, right? Because after multiplying this matrix to a vector, I have a vector of outputs, right? So there is a vector here, and then I'm going to compute a vector. Then I put one function, f, which gets one vector and returns again one vector. Clear? So this is what I am calling the vectorized or vector-activated neuron. So it gets a vector of inputs, compute a linear transform exactly like an artificial neuron, and then activate it. Everything is before, but instead of single dimension output, it now has multi-dimension output. Clear? Now, first thing first, if I have this matrix here and this bias here, do you think that I need to keep both of them here? No, I can always get rid of that guy with this dummy input 1, right? So I could say that this whole thing here is simply one larger matrix W multiplied with this X, which is basically the X itself with the dummy input 1, right? So this is what we used to do always. Now, I get this Y as the activated version of F, which is simply activated version of W times X, right? So I can do this. There is one key difference also here, and that is that this function F is not applying entry-wise anymore. Clear? So this function F is not applying on this Z entry-wise anymore. Before this, we always thought of scalar activation, meaning that if I give a vector Z, I simply pass every single entry of this Z through a function and then compute the corresponding Y, right? Now, I'm not necessarily doing that. Actually, I would never do it in such vector-activated neurons. I basically give the whole Z to this function F, and then this guy is going to compute the whole Y. So every single entry at the output, every single Y here, could be a function of everything inside this vector Z. Clear? So don't do the mistake. It's not anymore entry-wise operation. Clear? But beside that, everything is as before, right? So you have your X is getting passed. So if I want to just draw the computation graph, I have my X. I pass it through some W, which is a linear transform, and then I get Z, and then I simply activate it in a vectorized form. Clear? Any questions? Good. So now one favorite vectorized form or vector-activated neuron is the one which is activated by softmax. So how does softmax work? Softmax is of this particular form. So just to make it clear for you, if I have this vector Z, and this vector has C different entries. So it is Z1, Z2, and so on till ZC, capital C, right? So it has, for example, C is 10. We have 10 different entries here, right? And now, how do you compute your output if you want, you want to just activate it with this function F, which is now softmax, and then you want to get Y, which is of the same dimension now. So Y is again of C dimension. It has 10 different entries. If you want to compute Y1, for example, what you're going to do, you're going to get this guy, put it in the exponent. Okay? Look at this guy here. E to power this guy, right? So it's only a function of this one. But you just divide it by E to power exponent of every guy here. Clear? Yeah? Everybody got how softmax work? Yeah? So this is the softmax, and the key feature of this guy is that if you add it up over every single entry here, you're going to end up with 1. Great. Yeah? So let's just check it together. So say I have activated Y with softmax, meaning that I just pass this vector Z over softmax, and then I get Y1 till YC. And now what I want to do, I want to just add them up, right? So if I add them up, it's going to be the summation of this expression. This is basically the expression for softmax. You just pay attention that you are just doing the summation over this index C, not index J, because in the denominator you have already summed up everything. So it doesn't depend on C anymore, right? So if you do that, simply it is same summation in nominator and denominator, and it's going to be simply 1, right? Now, one other question. can y be anything negative? No, because it's exponent, right? Exponential function, e to power something. Exponential function is always positive. Can it be more than 1? Of course not, right? It cannot be. So it basically has this property of a probability distribution, right? So the output of softmax is basically a vector of probabilities. You add them up, it's going to be 1, and these are non-negative numbers, right? Clear? And this is basically what we want, because at the end of the day, we want to compute a distribution over our classes, right? Now, if you want to just simply extend the previous idea, which we did with the sigmoid function, to the case with multiple classes, the only thing that we need is to just remove that single neuron output layer and replace it with a vector-activated neuron, which has activation function softmax. And if you do that, then at the end of the day, you are going to get a bunch of numbers, y1 to yc. And these guys are probabilities, meaning that you're computing a bunch of probabilities. So you get numbers between 0 and 1, which add up to 1. And then you can just train this neural network such that it gives you the highest probability for the corresponding label, right? So if you put image 0, handwritten 0, then the first entry has the highest value. Everything else is small, right? And then you're going to say that, OK, the highest probability is that this input is handwritten 0. So I'm going to say 0, right? Clear? OK. Now, if you want to just try the forward pass, it's going to be nothing specific. It's exactly as before. So I am going to just pass it through one linear layer, then activate it. The activation here is entry-wise by ReLU function. Again, I pass it through another linear layer, and again I activate it, again entry-wise. But in the output layer, I am going to pass it through one linear layer. I mean, before we had a vector here. Now we have a matrix. So it's going to be a linear transform. And after that, we are going to pass it through softmax, yeah, which is a vector activation now, right? And then we're going to get a vector y. And then out of y, we are going to just compute the loss between this output and the corresponding true label. I'm going to talk about it, how we can do this, OK? But, yeah.
Is the loss just, when we take the label, is it just the one that we choose to be the most likely?
No, we can compute like MSE or cross entropy. We're going to do that, in other words. Yeah? But the key point is that in the forward pass, you basically need to know Z1 till Y3, right? And for now, I mean, we can compute everything. So basically, this is the same forward pass as we had in the binary classification. The only two differences are that we now are replacing the matrix of the vector of weights with a matrix of weights at the output layer. And then we do softmax activation, which is not an entry-wise activation anymore. Clear? And we do need it because we need to calculate a probability. You cannot do it with entry-wise activation, right? Clear? Cool. So now, if you want to just write down the math, I mean, you can definitely do it. So you start with your any input. So say you have one particular data input xb. You're going to add the dummy variable, pass it through your first linear layer, activate it. Then you go for the second linear layer. Then you activate it. And finally, you pass it through softmax. Now you have your probability y3, right? And once you have it, you need to compute the loss and be able to move backward, right? Pass backward toward the input so that you can compute the gradients now, right? Clear? So now, if you want to compute loss, this might be a question for you, how we can compute loss in this case. We basically need to just extend the idea that we had before for the binary classification. So what did we say in the binary classification? If I have label 1, how do I interpret it in the binary classification when I want to compare it to the probability? Do you remember? So we talked about this. If I have a binary classification, then my v, which is the true label, it could be either 1 or 0, right? And then we said if v equals to 1, then what do I say? I say the probability of v being 1 is 1. What is the probability of v being 0? It's 0. And then I told you I just replace it with v, and here 1 minus v. Then for any v, I do have this interpretation, right? So the probability of v being, for example, 0, if v is 0, then the probability of v being 1 is 0. The probability of v being 0 is 1 minus 0, which is 1, right? So we just interpreted that guy as a probability. Now, if I have 10 different classes, then can I still interpret my class or my true label as a probability? If I have 10 different classes and my true label is 10, what is the probability of my label being anything but 10? It's 0, right? The probability of if I have 10 different classes, so if now v instead of 1, 0, it could be 10 different classes. So it's 0, 1, 2 till 9. Okay? So I have 10 different classes. Then what can I say? What is the, now, if I see that my v equals by 3, then what would be the probability of v being 0? What is it? If I see the true label being 3, what is the chance of my true label being 0? 0. What is the chance of my true label being 1? What is the chance of my true label being 2? What is it? Sir? It's 0. What is the probability of my true label being 3? 1. What about anything after that? 0. Great. So I can again interpret this true label as that. Yeah? I could say, what is the number of the label? Yeah? The probability of my label being that is 1. Probability of my label being anything else is 0. Right? So what I can say like I can look at any image in my data set as a kind of random thing, random object. And then this random object has one class, right? And then I just compute the probability of this random object being in one class, right? So the probability of image being in class 1 is the first entry. The probability of image being in class 2 is the second entry, and so on till the last guy, right? Now, if I see that I have labeled VB for one particular image, so I look at one image in my data set, and it says that this image is in class 3. Then, what is the chance of being in class 1? 0. Class 2, 0. Class 3, 1, right? Anything else? 0 again. So you're going to have such a vector of probabilities, right? So if you see VB as your class, you're going to say your vector of probabilities is a vector of dimension C whose entry VB is 1. Anything else is 0. Do you know what we call this vector? One-hot vector, right? So this is what we call it, the one-hot vector. Okay? And if you do know that your label is V, then the corresponding probability vector is one-hot vector at index V. And what I'm going to show it with this guy, so 1 indexed by V. And what do I mean? I mean that this is a vector of the same dimension of the number of classes that you have, so this number C. And then any entry in this guy is 0, but the entry whose index is V, right? Now, for example, say I want to say my number of classes, C, equals by 3. Then any one-hot vector, 1V, What is the dimension of this vector? 3, right? So it's going to have 3 entries. All of them are 0 but one of them, right? So if I want to just write down 1, 2, what is it? 0 is index 1. 1 because index 2 is indicated here. 0. So you got the idea, right? So you have this example. So if C equals by 3, then 1 at index 1 has 1 here, anywhere else 0. 1 at index 2 going to have 0 everywhere but index 2, and so is for 1, 3. Clear? And then this 1v is going to be the probability vector of your corresponding label. Clear? So you can again interpret it exactly like what you did in the binary classification. You can again interpret it as a vector of probabilities. So you get the label, and then you just convert it into a vector of probabilities, right? So moral of the story, the true label V is simply telling you that the probability vector for your image inside your data set or your data point is simply the one hot vector at index V, right? Clear? So any questions? Now, if I have one hot vector as the probability vector and I have y3 as the probability vector that I got out of my neural network, then I can compare them now, right? Because both of them are probability vectors with same dimensions, right? I can just compare them. And then this is again the question of taste or your choice, which kind of loss function you are going to choose to compute the difference between these two probability vectors, right? So one choice that you can go ahead with is simply to just go for a squared error, meaning that you compute the MSE, simply just compute the norm of the subtract of these two vectors. This is one choice. But we talked about this, that the typical choice is the cross entropy because of that sort of, harsher punishment in the wrong classes, right? So you can, again, do the same thing as before. So if you want to compute MSE, you basically just get your output of the neural network, and then you compute its difference with this one hot vector, right? And then you compute the norm. It's going to give you the loss. And then you can simply say that since this is a one hot vector, this is basically 0 everywhere, but at the index V, meaning that every single guy at the output going to get a squared without any subtraction. The only guy that is getting subtracted is the one at index V, right? And then you can simply get this expression. You can compute the gradient of your loss. Now you don't have derivative anymore. You have a gradient, right? Because your input y is a vector. Your loss is a function of all of those entries, right? So you're going to compute a gradient, which is the vector of partial derivatives with respect to every single entry in your vector y, right? So now you're going to have the gradient. You can compute it analytically. If you go for cross entropy, you can again extend the idea as before. So if you remember, what was the binary cross entropy that we had? Do you remember the binary cross entropy? So when I wanted to compute the binary cross entropy, so I'm going to put B here to just indicate this is the binary cross entropy between y and v. And y and v, both of them, are scalars or vectors? Scalars, right? This is a binary case, right? So this is the output of the sigmoid function. This is your true label, right? And then how did we compute that? Do you remember? So it was minus v log of y minus 1 minus v log of 1 minus y. This was your binary cross entropy. Clear? Right? Now, what is this v? Okay, just let me see if I have any other color. No, we don't have. What is this v here? This is the probability of being 1, right? So this is the probability of your class, or v, being 1. Or let me write it down like this. Class being 1. What is this 1 minus v then? What is this guy? When this is the probability of your class being 1, this is class being 0, right? So the probability of your class being 0, right? So you have a vector of probabilities of dimension 2 here, and then you basically get the probability of your class being 1 in your true data set with your true label, multiply it with the log of the probability you have computed. Again, the probability of being 0, class 0, then multiply with the log of the probability that you have computed. Same thing you can extend here, right? So you can write this guy down in this form, meaning that you get your 1-hot vector, which is the vector that gives you the true probability vector, and then you multiply every single entry there with the logarithm of the output of your neural network, right? So it's the extension of the same definition. Here is binary. Now you have it in the multi-class case, right? And then you have this minus here, of course, as the one here to just keep it positive. And of course, this 1-hot vector entries, they are either 0 or 1. And basically all of them are 0, but the one which is exactly at point v, right? At index v, right? So this is going to be of this form, which you can simply simplify it. So you basically can say that this is minus logarithm of the y, which is at index of your true label, right? And this was the same thing again here, right? So if I put v equal by 1, then it's going to be minus logarithm of y. So it is minus logarithm of the probability you computed for class 1. And when my v is 0, this guy disappears, this guy shows up, and this is again minus logarithm of 1 minus y, which is minus logarithm of the probability you computed for class 0. Now, here it's going to be minus logarithm of the probability you computed for class v. Clear? Yeah.
Just to confirm, why is the probability from like the softmax?
Exactly. This is the output of the softmax. Exactly. So yeah.
What does it mean if I don't use the softmax values, but I use the largest value from the softmax activation?
Yeah, you basically do that because you want this guy to be positive, right?
Yeah, but can I do that? Does that make any difference if I use the cross entropy loss?
The cross entropy, I mean, if you take the things before activation, it could potentially be negative, right?
No, I mean after the softmax activation.
Okay.
Like for example, if class 3 has the largest probability,
Yeah.
0.53
Yeah.
out of all the 10 classes,
Yeah.
and then so basically that's a better explanation. I basically do the 1-hot for the y vector.
Exactly.
So will that affect the cross entropy loss?
No, it's going to be the same thing. I mean, it's the same. You're going to end up with the same expression in that case. But you don't take the maximum one. What you do, I mean, you are training. So you look at the output of your softmax. And you say, OK, the true label is 3. Okay? So I'm going to look at the probability at index 3. And I calculate minus logarithm of that guy. Okay? Or logarithm of 1 over that guy, actually. Yeah? Now, what I'm trying to do, I'm trying to minimize this one. So maybe when you start, that probability is very small. Yeah? But when you keep on training, that guy is going to increase more and more and getting close to 1. And you basically can simply see that this guy is going to get, again, minimized, same as what we did in the binary case, right? When that probability is exactly 1. Because this is potentially non-negative. It's going to be 0 only when that y is exactly 1, meaning that the output of your softmax is exactly what you have in your data set.
So cross entropy can be used for both softmax values and also the hard label.
Yeah, sure. I mean, but hard, you mean that you just look at your corresponding label and you take it. Yeah, this is the same thing, basically. Basically, this is the same.
But for the softmax one, it will penalize the model more if it's very uncertain, it has just very uniform
Yeah, no, the fact that you are taking this softmax version is basically because you want to convert it into a probability. If you don't have probability, then you could potentially get into analytic troubles. Like you cannot compute the loss. I hope it is clear what I'm saying, but if not, then we can discuss it later. Yeah, sure.
Now, we had a plot with a binary class entropy, which we could see, for example, when our choice is 1, but
Yeah.
we estimate it as 0,
Yeah.
It would be very high loss. Can we also see something like
Sure, definitely. I mean, you can just change V from the first class to the last class, right? And then, I mean, any of them is 0. So if you want this guy, I mean, basically, your logarithm is, or your loss is going to be only depending on the corresponding output, right? And then your hope is that this loss is minimized. And the minimum is 0, right? Meaning that you want this y to be 1, right?
Yeah.
And then when this y is 1, any other y should be 0, basically, because they add up to 1, right?
Yeah.
So it's the same thing, same idea. But now you have it in multidimensional case.
And when we are in a correct place, our loss would be in a minimum amount. Yeah.
When we are in, sorry?
In a correct place, for example, when when v is 1, and for example, the third one is 1, and
Yeah.
also we are estimating that correct, our loss in a minimum amount.
It's minimum amount, yes, but it's not the only thing. I mean, you need that value to be very close to 1, right? So if you want to what you want to see at the output of your neural network at the end of the day is that you want to see something like this. So say your V equals by 3, and then you have 10 classes, right? So what you want to see, this is your Y. You want this guy to be close to 0, this guy to be close to 0, this one to be close to 1, because your true label is 1. This is your y v, right? And then other guys to be 0, right? So you want this. But what would happen when you start, that maybe these numbers are not like that. So maybe this guy is 0.8, this is 0.1, this is 0.005, and then this guy is, I don't know, 0 point something, and so on for all of them, right? This could be the case. Then you're going to see that, okay, yv is this guy, and you compute log of 1 over this one, right? So minus logarithm of 0.005, and you see that this is a large number. So your gradient going to help you to just make this smaller. Meaning that in the next round, when you compute the output of your neural network, probably this guy is now larger. No, this is maybe 0.1, and then these guys have reduced. So 0.7 maybe, 0.005, and so on, right? And then again you see that, okay, this is better, so I got a smaller loss, but it's still large, right? So again, you keep on doing this. And gradually this guy increases, these guys going to reduce. At some point this is going to be 0.00 something, all of them going to be small, and this is maybe 0.99, so on, right? And then you would stop training. And now if you give that image to your neural network, it's going to classify it as class V, which is the right class. Correct? So everybody's clear about the cross entropy? Cool. So again, you can compute the cross entropy, and if you the gradient of the cross entropy, and it basically is again 0 everywhere, but at the index that you are computing it, right? And at that point, it's simply 1 over y. Yes, minus 1 over that value, that probability, right? So again, you have analytic expression for the gradient of your loss, right? And doing that, now you can simply do your backward propagation. So how you can back propagate over this network, you're going to start with the r hat, the loss. So you started with your data, and then you just pass forward everything over this network, and then you computed y3. Right now, if I give you the true class, you do know how you can compute the loss. For example, you go and compute the cross entropy. And then once you have the cross entropy, you have the loss, right? You have the loss for that particular point. And then you start just passing backward, right? So you start with one backward pass, you get from this loss into this guy, you just compute this gradient. You can compute this gradient. Simply you put this guy, for example, right? So you can compute this guy. And then the next thing that you get from y3 to z3, right? Oops, we don't know that one yet, right? So this is one thing that is missing yet, right? So we need to learn it. This is the last bit. But if I do know how I can get from y3 to z3, meaning that starting from the gradient of the loss, or this r hat b, with respect to y3, if I do know how to get back to the gradient of the loss with respect to z3, then everything else is obvious for me, right? Because everything else is either a linear transform, which I do know that I should multiply in the backward pass with the transpose version, or it is a entry-wise activation, which is going to be entry-wise product to the gradient, right? And I can go backward as that. So the only thing that I don't know exactly is this guy, this number 2. Okay? I don't know how I can get from y3 backward to z3 because I have a softmax here, and for one time more, this is not an entry-wise activation, right? So it is a kind of vector activation. And it's different from whatever we have done up to this point. Clear? Now, if that is clear, then let's just check how we can do the backpropagation on this particular step. Okay? If we know that, then everything is over. So again, we can just formulate it like the local operations we talked before, right? So we don't really need to look at the whole, messy picture. We can just focus on the part that we really want. How can I do that? I can say, okay, I have the r hat, which is the very last guy, right? And then I do know how I can get from r hat to y, meaning that I do know what is the gradient of r hat with respect to y. And now what I do now also is that there existed one z, and then I pass this z through some vectorized function, and then I got y. Clear? Now, I just want to know how I can compute the gradient of r hat with respect to z now. Clear? So again, I break it down to a local operation. So if I can resolve that, everything is over, because then I have the whole pass completed, right? Yeah? So this is the key point in the backpropagation. You always have just local operations. And if you can resolve one of them, then you just concatenate everything. You have the gradient, right? So now, we can, as I told you, whenever you get into such problem, just write down in this form, and then you can open it up, right? So I'm going to do it for you right now, but I mean, this is just a practice. I mean, of course, I do know that all of you use PyTorch to compute all of them, but at the end of the day, whatever it is, you do need to have the idea how you can do it, because I mean, just imagine a day without PyTorch, right? You need to compute it, right? So now, let's just look at it together and try to solve it together. So say I have this, so y, which is a vector function of f, so you can see it here. So I have y1, y2, and so on till yc, right? So I have c different outputs, c different probabilities. These are output of my softmax. So these are the output of, say, for example, softmax of this other vector z. And this vector is again z1, z2 to zc. Yeah? And what I do have the gradient of my r hat with respect to this vector y. And by vector y, I simply mean this guy. Okay? So what is this vector? This is basically the partial derivatives, right? So it's going to be the partial derivative of r hat with respect to the first entry, and so on till the last guy, yeah? So these partial derivatives, right? Now, what I want to do, I want to compute the gradient of r hat. I'm looking for the gradient of r hat with respect to z, which is again a vector of partial derivatives with respect to those z values, right? Correct? Now, what I should do, I should just focus on one of these guys and see how I can write it down, how I can write this guy in terms of these guys. And what should I use? Y? No, this is not the case. Just be careful. Here, y1, is it a function of z1? Yeah? y1, is it a function of z1? It is. I mean, it includes z1, definitely, right? Just think of softmax. How does y1 look in the softmax? So if I put f to be exactly softmax, what is y1? What is it? It's going to be e to power z1 divided by e to power z1 plus e to power z2 plus so on till e to power zc, right? This is your softmax output, correct? Now, is y1 a function of z1? Is y2 a function of z1? Yes, it is again. Because for y2, if I want to compute y2, the only thing changing is the denominator, right? So again, y2 is a function of z1 because z1 shows up in the denominator, right? y3, is y3 a function of z1? Everybody here is a function of z1, right? So if I want to compute, oh no, let's see. Yeah, okay. Oh, sorry. If I want to compute the partial derivative of r hat with respect to z1, and I want to use chain rule, what should I do? Let me do it that way. I know that you got the idea, but let's say here this is the guy z1, right? So z1 is going to show up in y1, right? It's going to show up in y2, right? It's going to show up in yc, all of them, right? And then all of these guys together are going to compute r hat for you. Now, if you want to just write down the chain rule, what should you do? You're going to say the partial derivative with respect to z1. This is, okay, I'm going to get from r hat first to y1, and then from y1 to z1. So it's going to be the partial derivative of r hat with respect to y1 times the partial derivative of y1 with respect to z1, right? So just get from this point here, and then from this one here. But this is not the only path, right? I get from r hat also to y2, and then from y2 to z1, right? So I can say plus partial derivative of r hat with respect to y2 times partial derivative of y2 with respect to z1, correct? And I keep on doing like this till the very last guy. So r hat with respect to yc times yc with respect to z1. Clear? So if you want to compute your gradient, you basically need to write down something like this. And I can represent the whole expression if I just define this Jacobian of a vectorized function. Okay? So everybody got the idea how I can do the backpropagation or write down the chain rule? Yeah? Everything clear? So now the only thing that you need to do is to just do a bunch of definitions. So for those of you who forgot this definition of Jacobian, you can simply define Jacobian, which is basically the collection of all of those gradients for your functional vectorized function. Okay? So if you look at this vectorized function y, every single entry in this vectorized function, y1 till yc, all of them are function of everything at the other side, right? So y1 is a function of z1 to zc, y2 is a function of z1 to zc, and so on till the last one, right? And then what you can say every single y, so yj itself has a gradient with respect to z, correct? Because y1 is a function of everybody. And then if you want to compute the derivative, you have partial derivative with respect to every single guy at the other side, every single z, right? So you're going to have this gradient for every single guy here, but now you don't have one gradient. You have c different gradients at the output, right? And then you can just collect all of them into one matrix, and then you call it Jacobian. Correct? Clear? So Jacobian is just the collection of all of those gradients, which are for the entries of your output. So if I compute the gradient of y1, I just put it in the first row, gradient of y2 in the second row, and so on till the last guy. Okay? And now, if I get back to my own problem, if I want to compute the partial derivative of r hat with respect to zc, so here you have it on the board for z1. If you just replace this z1 with any zc, then you basically can write it down by chain rule in this form, right? So it's going to be the partial derivative of r hat with respect to every single y that you have, r hat with respect to y1, r hat with respect to y2, and so on till the last guy. And every single of them is going to be multiplied with the partial derivative of the corresponding y with respect to your target zc. Clear? And if you just write it down in this form, then you can just modify it and write it down in the vectorized form. Clear? So you can just say that, okay, these guys, so this is the partial derivative of r hat with respect to y1, y2, and so on. So this is basically the gradient of r hat with respect to y. So every single entry here, first entry, is the entries inside the gradient of r hat with respect to y, which we already have it. And the other guys are the corresponding entries inside your Jacobian matrix. Okay? So you can simply, if you compare this guy, so look at this, this is the gradient of y1 with respect to zc, till gradient of yc with respect to zc. And if you compare it with this guy, this is going to be basically one of the columns, right? And then the only thing that you need to do now is to just multiply the Jacobian matrix with this gradient, but you should do the inner product. Yeah? So you can just double check the math afterwards. So you can simply see that this is basically your Jacobian that you have computed transposed times your gradient. Clear? So if I want to move backward over any vectorized neuron, the only thing that I need to do is to just compute the Jacobian, right? And then you can simply move backward by multiplying the transpose of the Jacobian to the previous gradient. So this is basically the extension of the ideas we had before. Okay? So you basically get your gradient, and then you multiply it with the transpose of Jacobian, and then you are back at your point z. Yeah? And you can keep on moving backward. Everybody's clear?
Just to be sure about the rows and columns for the Jacobian, because in my head the Jacobian, the line corresponds to the entry of f.
No, I mean, this is the standard way of defining it. I mean, here you have a square matrix, of course, because the number of outputs and inputs are the same. But typically, when you have different dimensions, then you put the number of rows to be the dimension of your output, the number of columns to be the dimension of your input. Yeah? It doesn't matter. I mean, if you define the transpose version of this guy to be your Jacobian, then you do the same thing here. Instead of having transpose, you just multiply it with that kind of Jacobian you define. So you don't need to confuse yourself with those stuff. I mean, you do know at the end of the day what we're doing. It's basically chain rule, right? So it's just your definition. But the key point is that you need to have the Jacobian, and then you multiply the Jacobian, the inner product, with your previous gradient. Clear? Any questions? So, moral of the story, backpropagation is important, right? Okay? So, backward pass over a vector activation is possible. So just to make it clear for you, you are not, I mean, I don't expect you to do all of the math immediately, like on the fly. I don't want that. I do not. I mean, if I were you, I cannot do it. Sometimes I cannot even follow the slides. That's fine. I hope you get the idea that, okay, if I give you this guy, you can move backward, right? And that is okay, because at the end of the day, you are going to use something that does it automatically for you. But the point is that you might get into a point where you have a new operation. I mean, as you see through the course, you're going to see that there are lots of new operations coming up, right? So after this one, we are going to get into convolution. And then we're going to go into recurrent neural network, gating, things like that, right? And all of them are new ideas that people thought, okay, if we do that operation, it's going to make sense in generating related information. But it's not simply that, okay, I can just put that new operation and that's it. I need to be able to move backward over that as well, right? And there is, of course, nothing you really cannot move backward, but you need to have the idea how easy it is to just move backward over that, right? Clear? So sometimes the derivative does not exist. Sometimes it's really computationally hard to do that, so you should be clear. Yeah? And in reality, on back scene of your computer, all of these things are happening, right? And as engineer, you need to know what is happening behind the scene, right? So, moral of the story, when you are moving backward with a vector activation, you just multiply with the Jacobian, which is a kind of extended version of what we had up to this point. And if we do that, then the backward pass is now completely clear, right? So you start with the loss, and then you compute the gradient, and then you compute the Jacobian, multiply it with the gradient in the previous pass, and then you just again pass it backward, you multiply it with this W, and you keep on doing this till you get to the input. And once you have all of those gradients, so you have gradient with respect to every single z, then you simply can compute your gradient with respect to weights, because as you remember, the gradient with respect to weight is simply your activated vector outer producted with those gradients with respect to z. Okay? So that's going to be it. Now, what you have done, or what we have done together, so you cannot run away from it. So we are all together in this. So what we did here, we basically have trained a kind of feed-forward neural network, fully connected feed-forward neural network, for a multi-class classification. And if we want to just write down the whole gradient descent loop, then we basically start with some initial stuff. Then for every single point inside our data set, we are just moving once forward. We do know how to do it. We compute the output of the softmax, and then we move backward. Again, we know how to do it, right? And then when we get backward, then we have the gradients. So we have these gradients, these G matrices are the gradients of the corresponding W matrices. Yeah? So we compute those gradients, and this is the gradient for one single point, right? And you keep doing it for all points inside your data set till this is completely over. And once it is over, you are going to just average those gradients. And this is now the gradient of your empirical risk. So you are going to update your weight with the learning rate and that gradient you computed. Clear?
Sorry, why did you get some mean?
Because every single G of B, all of them, it is computed for one single point, right? And by mean, I mean the average one. Because at the end of the day, I mean, your R hat, your true R hat, we define it to be the 1 over B, number of data that you have, times summation of R hat B, right? B from 1 to B. Clear? Now, what you want is the gradient of this guy with respect to those W's, those weights, right? And what you do in each forward-backward pass, you compute the gradient for that particular B with respect to that weight, right? So once you're over with all your forward-backward pass, then you have all these gradients. So this is what I showed you as GB, right? And then you just average it, yeah? You compute the mean. So then this is going to be your gradient of the empirical risk, gradient of R hat, and then you're going to just update your weights. Clear? Yeah.
And the mean of a lot of matrix is just for element.
Element-wise, exactly. Yeah.
Okay.
So Everybody's clear? Great. So this is what we call it full batch gradient descent. So this is the perfect thing you could do, but as you might guess, we cannot do it because this is going to be too much computation. So we're going to have a 3 minutes break, right? And then after that, we're going to see how we can deal with this full batch issue. So thanks. So shall we go on? No. Okay, so full batch training, it simply means that we should go over the whole batch of data that we have, right? And this is, I mean, it's a very good idea if we could, but we cannot. That's the point, right? Why we cannot? Let's just make it clear. First of all, as I told you, batch, in this course at least, it means the whole data that you have. And you are using it for training. Okay? So the whole data that you are using for training, this is what we call it, the batch of data. Okay? So the batch is the whole data set reserved for training. And then if you want to do full batch training, it means that you should start with the first point in your data set or training data set. You just go over it forward, backward, and then again, next point, forward, backward, and so on till the last guy in the batch. Once all of it is over, then you can compute just one gradient. You do one iteration of gradient descent, right? And then again, you get a new weight. You just put that on your neural network. Again, you start with the first guy in the batch, forward, backward, and so on till the last one, and then you do your next iteration, right? So this is the idea of full batch training. And one thing that you might ask me right now, I guess most of you have the idea after assignment 1, but you might ask me, you are saying any data point or the part of data set that has been reserved for training, don't we use all of it? And I guess most of you have the answer. No, we don't use all of it. We just reserve a part of it for testing later on. So this was what you did in assignment 1. After you trained your linear model on the synthetic data you generated for that particular projectile problem, then when you wanted to test it, you had to just generate one independent data set. And that makes sense because if you test it on the data set that you have minimized the loss on, it's going to work perfect, of course. But you don't want that. You want to be sure that if you get a new data, then this guy is also getting classified or whatever the neural network does properly with this neural network, right? So we are going to put a part of it, reserve a part of it for testing later on, okay? So I guess you have the idea, but if not, no problem. We're going to talk about this. But the whole point is that right now we have a bunch of data, and then we are going to use it for training, and we need to go over it completely to just do one step of gradient descent. This is not very feasible thing. So you might wonder why this is not feasible. I mean, how much data we could have. Just let's look at one particular example. So this is the example of image classification, and say we want to do image classification with the same problem we just dealt with just a couple of slides before. So we basically get image of a handwritten number, handwritten digit, and what we want to do, we want to, or output of your neural network, like what we had in the previous slides, to give us the true class of that image, right? So if you want to do the training, you need to have a bunch of images of handwritten numbers, right? And then you either go ahead and do collection, so you ask people to just write down different digits, and then you just label them. So you would say, okay, number 0, this guy has written 0, this is 0, so this is going to be labeled 0, and so on. This is one way that you can do it. Or you can just rely on the public data set. For example, MNIST. So this is the simplest data set you can get for image classification problems. Okay? And basically some bunch of people at this National Institute of Standard and Technology went on, asked every single kid to write down a digit, and then they just took them, put them in 28 by 28 pixel images, and then they labeled them. Like, this kid has written 1, this kid has written 2, and so on. So if this is available public, you can access it. And just, this is not the only one. You have, probably you know about lots of other public data sets. For example, CIFAR is the Canadian version of it, where you have images of different objects, like car, cat, dog, things like that. And then we have CIFAR 10, where we have images of 10 different classes. And then we have CIFAR 100, which is images of 100 different classes. There is the other one, ImageNet, which is the famous one because it was the kind of data set people use for ImageNet challenge. We're going to talk about this in chapter 5. And there are a bunch of other data sets, like Caltech data sets, and also the FashionMNIST, which is the, say, recent version of MNIST. So you have a bunch of clothings, like shirt, trousers, I don't know exactly the classes, but a bunch of classes of different clothings, and you want to do the classification, okay? So you have this data set, and you can always, you can check them online. There are a bunch. If you have not heard of them, go ahead, just click on this online, go ahead, check the public data set that are available. And if you are doing your assignment too, you already know how you can access them. Basically, by PyTorch, you simply can access them because Torch Vision lets you just load them on your computer, right? You just go to Torch Vision datasets, and then you load that particular data set. So, but all, back to our problem. Say, for example, we want to do that problem, and what we're going to do, we're going to go over MNIST, which, as I told you, is a 28 by 28, or data set of 28 by 28 images of handwritten digits. And every single image, you can just show it in one long vector. So it is 784 dimensional vector, because 28 times 28 is simply 784. So you have 784 different pixels in each image. You can put them in a vector, and then you get this vector, pass it through your neural network. At the output, you get a vector of dimension 10. And the first class tells you it's 0, second class tells you it's 1, and so on till the last class, which tells you it's 9, right? And the thing that you want to do is that when you just put the pixels of number, for example, 3, then the fourth class at the output gives you the highest probability, right? So that is the problem that you want to do. And now let's see, if you want to do the full batch training, how much computation we need to do. So this MNIST data set has 70K different images. And if you want to, typical approach is that we keep 60K of them for training, and we reserve 10K of them for later testing. So after we just trained it over that 60,000 images, then we give 10,000 images to just check these new images, whether they are being classified correctly or not, okay? Now, our batch has 60,000 different data points, right? And if you want to just do full batch training, it means that for every single iteration of your gradient descent, you need to do 60,000 forward-backward passes. Clear? Which sounds quite large. Yeah? So if you say that you need to have 100 different iterations for your gradient descent to converge into some minimizer, then you're going to need to do 6 million times forward-backward passes in your algorithm, which is a lot. Especially if your neural network is very deep with large, layers, then you need to really do lots of linear operation in the forward and lots of linear operation in the backward, which could be really time consuming. So this is not a very good idea, and this is one of the reasons many people would have said many years ago, this is not really feasible to do, but we have a very simple trick for that. And the simple trick is that we just go for some stochastic version of the gradient descent. So this is basically what you probably have heard of. A stochastic gradient descent, I guess everybody has heard of. Some people call it a stochastic mini-batch gradient descent. This is a better version, which is usually used in practice. But we're going to talk about both of them, okay? But I hope you got the idea why full batch training is costly for us, right? We cannot go over all the data points in every single iteration. This is not feasible, right? So now, the very first idea that we can come up with is that, okay, if 60,000 of backward-forward pass is too much, what about just a single forward-backward pass? Meaning that I choose one point, one data point. I just do forward-backward pass. When I am over, I have a bunch of gradients. These are the gradients of the loss at that particular point. But what's going to happen if instead of the gradient of the empirical risk, I just use this gradient? They are of the same dimension, right? I can use it. Yeah? It might be that my algorithm doesn't work fine. Yeah? But at the end of the day, it doesn't impact the math of the problem. It's still a kind of gradient, right? So this is the most basic idea. This is what we call it sample level gradient descent. So you basically, what you're going to do, you're going to start with your first data point, okay? Your very first image in your data set. And then you keep on iterating, and each iteration, you just do one forward pass. So you get your first image, you pass it forward, you get the output, and then after that, you do the backward propagation, so you get all the gradients. And these are the gradients that you have computed for the loss of that particular data point, right? But you just ignore it. Yeah? You just forget about that. And you use that particular guy to just do the update. Okay? So you update all of your layers with that one-shot gradient that you have computed for one sample inside your data set. And then for the next iteration, what you're going to do, you're going to go for the next data point. So you're going to go for your second image. And then again, you're going to go forward, backward, you get gradients, you update. You don't wait for all of them to be over. You keep on going, right? Clear? So you got the idea? It does work, right? Yeah. Yeah, many people said that it works. I mean, of course, we don't use it in practice like this. I mean, we just make mini batches. But, I mean, potentially it could work in many problems. You can, because potentially, I mean, we're going to see it like in a few slides. I try to explain it. But the point is that, like, if you do full batch training, you are saying that, okay, I'm going this way down on my loss. But now you're doing it like this. Yeah? But at the end of the day, you are going to converge. So it's going to happen. Yeah? Because you get 60K times more boost in your algorithm. You can do much more iterations, right? Yeah.
On line 9, you have sample level update. Like, is there any sampling going on? Or?
Yeah, sample, because X is one sample in your data set, right? So you compute your gradient for one sample, one data point inside your data set, and then you update, right?
But are you sampling that? Like,
not sampling, I mean, you're taking that from
you're just looping through every single data point.
every single data point, right? But every single,
You're not randomly choosing the order.
we're going to do that, yeah.
Oh,
Yeah, but not right now, no.
Not right
Right
now.
now, no. I'm just starting from the first sample inside my data set. I mean, sample, I simply mean the data point. Sample, and then go on with the next one, so on. Yeah. Yep. Yes. Yeah, and we are going to do that next.
From a certain data point that's entered to the network, and from the output to that network, there are multiple paths. Like there are so many different paths. Is the path also chosen randomly?
No. You compute the whole thing. So you start with your data point. You do all of those multiplication and activations. Then all of them, of course. I mean, that one is, but that is not a big deal. I mean, even if your network is very large, it's just one-shot linear computation. You can always do it.
The data point is only randomized.
Yeah. But if you want to go full batch, you need to do it 60K times with MNIST, right? Now you're just doing it one time.
60K is the size of the data set.
Data set, training data set, exactly. Yeah. So, any questions? So you got the idea, right? So now you keep on doing it, and what happens if you get into your final data point or final sample inside this data set, training data set, and you want to keep on iterating? What you would do? Start over, exactly. So if you end up with the whole points inside your data set, you again start over. You keep doing this, right? Clear? So this is what we call it sample level training, and this potentially can work, but you might just wonder why this should work, right? So what is the meaning? So let me just give you first one very dummy example. So what we basically are doing here, we are actually just approximating the gradient that we want to compute with the gradient that we get with only one sample, right? We're just doing this. And why should it make sense? Because because if you remember what we do, we basically go ahead and compute, if you want to do it full batch, we're going to compute this gradient for every single sample inside our batch, and then we average them, yeah? But what's going to happen if all of them are the same? Like just a dummy example, right? Every single guy is the same. So for every single data point, you go forward, backward, you end up with the same gradient. Then when you compute the mean value, it's going to be exactly every single of them, right? So what was the point waiting for all of them, right? So you could just immediately update in your first shot, right? Correct? So this is not really happening, but something in statistical form, something like that is happening. So if we really had this dummy case, this ideal case, then sample level training was basically the full batch training that we are doing right now, right? But in practice, this is not happening. In practice, what is happening is something like this. And now, that GL, the blue gradient that I'm showing you right here, this is like the ideal gradient that you wanted to compute, right? And now, I'm going to speak about it a bit later, okay? But say I wanted to compute that one. Every time that I go forward, backward over this neural network, I am going to compute a noisy version of that. Meaning that I'm getting the same guy, GL bar, this blue G, blue gradient, plus some sort of noise. So every entry has been moved by some noise. This noise could be potentially very large. This could be very small. Yeah? But at the end of the day, you can think of every single gradient sample that you're computing to be of this form. And what we are doing in this sample level approach, we're saying that every of these noisy guys is a kind of approximation of the true one. So is the average one. So what we do in full batch training, we are just computing the average of all of these guys. And again, the average of all of these guys is not exactly this target, the ground truth that we want to compute. Yeah? We are just getting close to that. Okay? And every single guy that we are computing is also, again, that guy with some noise. So what we say, okay, I mean, we cannot afford that much of complexity, so we're going to take this dummy approximation. Okay? And this dummy approximation is what we call it an estimator of our ground truth gradient. So we wanted to know that blue gradient. We just estimate it based on what we have. And what we have right now is just one single data point. So the only way that we can estimate it, just pass it forward, backward, get the gradient. That is your estimator of the true gradient that you want. And then what I'm going to do, I'm just going to say that this sample level gradient is approximately the full batch gradient, which is basically approximately, again, the ground truth that I want to compute. But in the sample level, I'm doing a very bad approximation, the worst approximation possible. In the other one, the full batch training, I am doing a much better approximation. And if you don't see it again clearly, I'm going to talk about this. Yeah?
Sorry, I have a basic question.
Yeah.
Previously, we had a delta, which was a summation of error between each single data point, the true label, and the estimated value.
Yes.
So here, in the sample level training, what is the convergence rule? I mean, what is
This is the same thing.
for the all data points?
No, for your loss.
So
I got your point. So you mean when we're going to terminate, right? Yeah, we're going to talk about this. So at the end of the day, you're going to terminate after a number of iterations. So you don't wait till anything converges, right? You're going to monitor everything, and at some point, you probably have seen these images of training, learning curves. Yeah? You get the accuracy, and at some point you say, okay, this is saturated, so I'm going to stop. So we're going to get over it, so no worries. But it was a nice point. Yeah, we're going to talk about this. So you got the idea what we are doing here? So we are basically just approximating or estimating or target gradient with this sample gradient that we have computed. Okay? Now, one issue that we can see in this dummy approach or naive implementation of sample level gradient descent is that we could potentially get into what we call it repetitive cycle issue. So it's again a kind of made up name. Okay, I don't know if it really exists, but you could get into a sort of repetition in the behavior when you are going over the same data set with the same order over and over. To just make it clear to you, let's just consider this very dummy example again. Okay, so what is here happening? I have one initial weight, say for layer L. I have an initial weight WL0. Okay, this is what I start with. And I start doing sample level update, meaning that I go over my first data point and then I compute the new weight, right? So I compute the gradient and update my weight, right? And I get this new weight. Now with this weight I go over my second data point, right? And then I compute again the sample gradient, I update, right? So I'm going to get the next weight matrix. Clear? And then I keep on going till I'm over with all of my data set, right? So now say that the number of iterations I want to do is more than the size of my data set, meaning that I am going to get back to the first point, right? And again do this. Clear? So I started with my first data point, computed the gradient, I got my first weight update. Then second data point, second update. Last data point number B, I got my last updated weight, right? Now if I want to update once more my weight, what should I do? I should go back to my first data point, right? Again, I compute the gradient for that one, and then I update my weight. Clear? But what's going to happen if this last guy is exactly the initial one? What's going to happen? So if this last guy is exactly my initial weight, then I am going to go, just instead of the 0, I can write B. And then I go again over my first data point, I get the same update, second data with the same update, and so on till the last one. You got the idea? What is the issue?
How can it happen?
It does not happen exactly, but it could happen approximately. Everything, you should think of it approximately.
This means that the variance of the risk is so large that
Yes.
we go like one step and then
Yeah.
the next function will.
Exactly. And the reason is because you have this loss function, which is depending on all different labels that you have, right? And then this loss function is something like this, but what you're doing, you have a high dimensional, like all of the weights involved. But when you are just focusing on one data point, you get just one part of this guy going down, right? So after updating, your loss function is now like this. But the next guy, when you go for the next point, it tells you that no, you should push this one down. And then you get again back to the original one. Okay? So they could impact each other like destructively. And this is the repetition that could happen in the behavior. Of course, it does not happen exactly with approximation, but you could have such a behavior. Yeah? And this means that if you have such, like in this dummy example, you would never change, right? Because you again start with the initial weight, and you keep on updating, then you end up with the initial weight, and you keep on doing. So if you do it forever, you always have your initial weight, right? Which is not a kind of good idea. Clear? So how we can resolve it? Any suggestion? Sorry? Yeah, random shuffling, exactly. So you can simply randomly shuffle these guys. So just to get over this kind of repetitive behavior, what you can do, you can go for shuffling. And if you do the shuffling, the algorithm I showed you is going to be a stochastic gradient descent. So this stochastic term comes from the fact that you are doing random shuffling. Yeah? So a stochastic gradient descent is basically the same thing as your sample level gradient descent. The only difference is that after you have gone over the whole data set, you just randomly shuffle everything, and now you start. And then you're sure that you are not starting again with the same point, right? And then, if you are here, if you start again, you get the same weight here, so the same initial weight. You're not starting exactly with the same point, so there is no reason you end up with the same weight again. Clear? Then potentially you could get out of this trap. So So this is the idea of the idea that we call it stochastic gradient descent, and this is the most common algorithm being used in practice. I mean, of course, modified version of it, but this is stochastic gradient descent, so stochastic plus gradient-based algorithms is the most common algorithm that you have used it in. We use it in training of neural networks. So you might wonder what exactly I mean by random shuffling. I simply mean randomly permuting those numbers, data points. So basically I can write the same thing as before. So this is exactly the sample level gradient descent that we had as before. And the only thing that now changes is this random shuffling at the beginning of each time I go again over my data set. So I start with my first data point. So this is sample level. I start with my first data point. I do one update, second data point. I do the next update, and so on until I get to the last guy. And once I got to the last guy, before I start with the first one again, I get my whole data set. I shuffle them, right? And then I get all of them permuted. And then I again start from the first one, so on till the last one, and then keep on doing that, okay? So that is going to be stochastic gradient descent. Same thing as before, only random shuffling at the beginning of each time you go again over your data set. Clear? Everybody has the idea what is stochastic gradient descent? Okay. So now you might ask me that, okay, you told us that by sample level training, we are winning in terms of complexity, and we are using an approximation of the gradient. But don't we lose anything? Because, I mean, there's no free lunch. Yeah? Always when you get something, you're going to lose something, right? So this is true. In fact, it's happening. Then there is a kind of clear trade-off between the sample level and the full batch training. And that is what we call it the variance complexity, estimation variance complexity trade-off. So to just understand this guy, let's just do a quick recap. Everybody is clear with the definition of variance, right? So everybody knows what is a variance. So if you have a random variable, just a random number, random variable x, and then you know that the mean value, the expected value of that guy is mu, you're going to subtract it from that expected value, and then you compute its power, right? Meaning that you just square it and compute the expectation. So you want to see how much energy the variation of this random variable has. This is what we call it variance, right? And you can simply show that this is basically the energy of the random variable itself, expectation of x squared, minus the mean value squared, right? And if you assume from now on that the mean value is 0, so it's a 0 mean random variable, then it's basically the expectation of x squared, right? This is your variance. And then there are a bunch of properties for variance. If I multiply x with one number, what's going to happen to its variance? It can multiply with the squared version of that number, yeah, right? So if I multiply x with some deterministic number c, a constant c, then my variance is going to be the previous one multiplied with c squared, right? Clear? If I have a bunch of independent random variables and I add them up, what is the variance of this summation? Is the summation of the variances, right? So not the summation or not the variance of every summation of random variables is summation of variances. This only happens when the random variables are independent, right? Because if they are not independent, all of those cross terms are going to show up, right? So if you have a bunch of independent random variables and you add them up, then the variance of these independent random variables is going to be summation of the variances, okay? So just as a recap. And now let's say I have a bunch of random variables, so x1 to xn, all of them independent, all of them have mean 0, and all of them have variance sigma squared, okay? Easy. Every single guy has mean 0 and variance sigma squared, and they are independent. What's going to happen if I compute the arithmetic average of them? Let's do it together, okay? What do I mean by arithmetic averaging? I simply mean this mean operation I show you. Okay? I get all of them, add them up, divide them by the number of them. Okay? So if I have n different independent samples, I'm going to just add those samples and I divide it by the number of the samples. Okay? I mean by arithmetic averaging that guy. Okay? Now, what's going to be the variance of this average? The variance of this guy, okay, I can simply use the properties we had in the previous slide. First of all, I can write it down in this form, right? So it's 1 over n, this constant, times this summation, right? Now, I'm going to keep this summation still inside the variance. I bring this constant out, which is going to get a squared, right? So it's going to be 1 over n squared times the variance of the summation. And what is the variance of the summation of independent random variables? Summation of the variances. And here, what is the variance of every single guy? Sigma squared. So this variance inside the bracket, the whole variance here, what it would be? N times sigma squared. So you can simply say that this is summation of every single variance. Every single of them is sigma squared. So it is going to be n times sigma squared, right? And then when you multiply it with 1 over n squared, then it's going to be sigma squared by n. Clear? Now what is happening here? So if you have a bunch of random variables and you add them, you're just, or compute the arithmetic average, yeah? Just compute the mean value. What are you doing? You're basically reducing the variance, right? And this reduction is happening with proportional to number of samples, correct? So what you can say is that if you do arithmetic averaging, you're basically dropping the variance proportional to the number of samples that you have, yeah? And now probably it rings a bell in your mind about what we did with sample level and with full batch training, right? So let's get back into this formulation I showed you. So I told you that we have a ground truth, that G bar, that blue gradient that we want to compute. And I told you that this is something ideal that we want to compute. We cannot compute it. What do I mean by that? So if you remember we initially said that we want to minimize the true risk. You remember that? When we started with the whole training procedure, we said that, okay, if we want to just mathematically do something meaningful, we should be able to compute the expected loss, which we called it risk. It was true risk, and then we just tried to minimize that, right? But we couldn't compute that. What was the reason? We didn't have the data distribution we needed. The second thing was that we didn't know the true function. I mean, if we would have known the true function, we wouldn't have done this. Yeah? So that was something, that true risk is something that I cannot compute. But what at the end of the day I want is the gradient of that guy, right? What I do in practice, I'm going to just approximate it with the empirical risk, right? And then the gradient of this guy is actually an approximator or estimator of the gradient of this true risk, which I don't know, right? So by this G bar here, I simply mean the gradient of that, ideal guy in the moon, which I have not access to. And what we are doing always, we are just estimating that. So every time I go forward, backward, I get a noisy estimate of that guy. So I basically get the guy plus some sort of noise. And you can again think of that noise to be a sort of independent random thing, random matrix here, being added to the true gradient that I want, and then it has some particular variance. I don't know what is the variance, I don't care. I don't know what is the distribution. Again, I don't care. The only thing that I care right now is that I can look at every single sample gradient that I compute as the true gradient that I want and I have no access to, plus some sort of noise. And if it's a bit tough for you to imagine of matrices, just think of these guys as numbers. No problem. It's not impacting your understanding. Okay? So you can think of gradient, all of them here as scalars. Okay? Now, what I do have here, I wanted to compute this G bar, and I couldn't, so what I did, I just went ahead and computed the gradient of this R hat, right? And what this guy ended up to be, so I computed this gradient. And what is this guy actually, the full batch gradient? This is basically the average of all of those sample gradients that I compute, right? So the gradient of this R hat guy, the green guy, which is the approximator, the estimator of the gradient of the blue guy I don't have access to. That is, based on the algorithm we developed, the average, arithmetic average of all of those forward-backward passes, right? Which is the average of all of these guys, G1 to GB, right? And now, if I write down this average, this is going to be average of these guys if I just replace every single sample gradient into that expression, right? And now, the first term, 1 over b summation of that blue gradient, what is going to be? It's going to be the blue gradient itself, right? Because that guy is fixed. It's not changing, right? So it's a fixed number. You add it up b times to itself. It's going to be b times that guy. And then you divided it by b, right? It's going to be the guy itself. So the thing that is coming out of it is this guy, this G bar itself, the true gradient that you want, plus the average of the noises. Now, here the average of the noises, what is the variance of this guy? If you know that the variance of every single guy is sigma squared, what is this one? Sigma squared divided by the number of data points in your batch. So here you have this error of your batch estimator, and this error of the batch estimator is actually dropping as compared to the error of every single sample gradient with proportional to 1 over the number of samples you have inside your batch. Clear? So now, when we are doing the full batch training, what we are basically doing, we are just reducing the error of our gradient estimator, right? If we are doing sample level, we get less complexity, but we have higher error in our gradient estimation. Clear? So both of them are basically doing the same thing. The only difference is that this other guy, this batch gradient or batch estimator of the gradient, this is a better estimator as compared to that sample estimator, right? But of course, to find it, you need more complexity, more time, right? So this is going to end up with this sort of trade-off that in the full batch training, you have sigma squared divided by the number of points that you have in your batch. But in your stochastic gradient descent, basically you have sigma squared, the original error, right? And to just have an idea how much they could be different, just think of the mini MNIST data set. So I told you have 60K data points. And the difference is of this order, 10 to the power minus 5. Okay? So you're going to get 10 to the power minus 5 less error in your estimation if you do full batch training. Yeah? But of course, you need to do 10 to the power 6 or 10 to the power 5 almost, yeah. 10 to the power 5 times more computation, right? So you're losing something, you're gaining something, right? So this is what we call it the complexity accuracy trade-off between the sample level gradient descent and the full batch gradient descent or full batch training. And if we want to just simply state it, if we spend time t for every single forward-backward pass, okay, then with a stochastic gradient descent, you just do update with every t seconds, for example, every time t. But with the full batch training, you just need to wait b times t till you can update, right? So your update is much faster in the stochastic gradient descent. But what is the price you are paying? The price is that you have much higher variance in every estimation that you are doing, in every iteration. Clear? So everybody got the idea? I mean, I don't really want you to just get the whole math behind it. I mean, obviously, I didn't bring you that much math here. But I hope that I could transfer the idea. because you might hear it a lot. Like you do the stochastic gradient descent, you are computing an estimator, unbiased estimator of your gradient. Yeah? And why you are computing that? Because you're basically computing that sample gradient, which is the original gradient that you want, you don't have access to, plus some noise, right? And this is an estimator. And it is called unbiased because basically if you just compute the mean value, meaning that if you have lots of them and you average them out, at the end of the day you are going to end up with your original gradient, which makes sense, right? I mean, if I have infinite data points, I basically can compute my true loss, and then I can compute the true gradient, right? But I don't have infinite, so everything is no approximation. So everybody's clear about the idea? So this is a kind of issue, a kind of trade-off that you have. So on one hand, you can be very fast using sample level training, but you have lots of error in each iteration, meaning that if the true gradient tells you you should go this direction, no, your estimator could just vary anywhere here, right? So if the true gradient tells you this is your loss, I mean in any space, I don't know, two-dimensional, so forget about this. But at the end of the day, your gradient is something like this. This is that G bar, right? So your gradient tells you like this, but when you do a stochastic gradient descent, you could get anything in this area. So it could tell you go this way, it could tell you go this way. But the good thing is that, I mean, instead of going that way, now you are going this way, but next time probably the error tells you go that way, right? And then it's going to just take you towards the minimal point. So I'm here, I want to get there. If I just use full batch training, I'm going to move like this. But if I just do a stochastic gradient descent, I just move like this. Yeah? By the end of the day, I'm going to end up here, right? Clear? So this is going to be the stochastic gradient descent. Now if I have, so this is SGD, but if I do the full batch training, it is going to have a smaller variation, right? So you could get something in this, no, it's too much, in this direction, right? So it is going to just reduce amount of, jiggling that you do towards your optimum point. So that's the idea of doing a stochastic gradient descent. The only thing that probably has come to your mind is that why we do just the two extreme cases, full batch or sample level. Can we do something in between? Of course you can do, and this is what we do in practice. So in practice we use mini batches, meaning that we get our whole data set and then we just split it into small mini batches, and then we use one mini batch to compute an approximation or estimation of our gradient, and then we do the update. We go for the next mini batch, do that, and so on. Yeah? So this is what we are going to have in the next session, right? Clear? So that's it for today.